All right. Good day, everyone. I'm Kerry Chingito from EQ4. Here to present the mathematical reasoning for GE Math MW. So let's get started. So what is mathematical reasoning? So basically, this is one of the most important parts in mathematics, considering that it determines the truth values of certain statements, right? So these statements are often found in exams, probably in your entrance exams, if you had any when you were in high school or even going into college, right? So we will be exploring the different concepts of said mathematical reasoning and learn different effective techniques for solving such questions with ease, right? So there sorry. So there's basically two different kinds of mathematical reasoning. The inductive reasoning, which is a process that essentially uses a certain formula, a theory, or some sort of generalization, taking into consideration certain patterns, right? So we'll be discussing this. I'll be showing you a diagram later, so you'll have a better understanding as to what inductive reasoning and deductive reasoning is. But going back, where on the other hand, deductive reasoning is basically using a specific instance or a premise to, arrive at a certain theory or generalization. So what's the difference between the two, right? So as you can see here in this graph, inductive starts with an observation, right? So when you see an observation, you recognize a certain pattern, and using that certain pattern, you find certain theories that would essentially make the most sense out of this said observation that you had, and eventually you'd be reaching a certain solution, a certain conclusion, right? And whereas deductive, as you can see, you actually start with a particular theory, and given that theory, you formulate a hypothesis and you collect data. Basically, something that you would generally do for research, right? So you look at the theory, you make an hypothesis, of course, you make a data, then you analyze that data the same way that you would analyze the pattern here in the inductive, and eventually you'd reach an answer that would either accept or not accept the hypothesis you made earlier in this procedure or experiment. So that's basically the difference between the two. And moving on, theorems. So what is a theorem? It's basically some sort of statement that that could be proven to be true, but of course it is from the word theorem, from the word theory rather. It isn't exactly considered as a fully graced truth. It's basically a working pattern for a certain situation, right? So it could be usually found in mathematics, science, or even actually in language, as again that pretty much fits the current chapter that we're in right now. And other than that, it's considered to be some sort of fundamental principle or again a foundational truth, but again it's not yet considered to be a fully graced truth unless proven otherwise. These are just patterns that work in most situations, right? Where it works so much that it might be considered as the truth, right? And one particular theorem that works for a lot of the one particular theorem that works in the previous video explaining the which is the roots of inference, which is used to tie together the steps of a proof, right? But more on that later. We'll be now tackling fallacies. So fallacies are essentially there's something wrong within a certain proposition or a string of propositions, or even even within the rules of inference, right? So there are different kinds of fallacies. Here we have three examples. One being affirming the conclusion. Basically, it's a situation where the conclusion is basically repeated, thus making it redundant, and it doesn't provide some sort of evidence or reasoning behind the conclusion, right? And it follows this compound proposition: P with the implication of Q, and Q with an implication of P, and that pretty much repeats, right? Anyway, the second example would be the fallacy of denying the hypothesis. It's basically a type of logical fallacy that occurs when one argues against a certain conditional statement by claiming the inverse of the statement being true, right? Basically, if you were to convert it into a compound proposition, it would be like this: P with the implication of Q, and not P with the implication of not Q, right? And the fallacy of and the last example would be the fallacy of begging the question, right? It's very similar to affirming the conclusion, considering that it repeats, but essentially it's where the conclusion is used to a premise in the same argument without again providing the same evidence or reasoning to support it, right? Going back to the theorem, right, the rules of inferences. So these are some theorems that actually work in proving certain propositions, right? So I've included here 8 examples. So Vocacious proof is basically saying that it's a conditional statement wherein it's true, but the hypothesis is false, right? Whereas the trivial proof, it's basically establishing the truth of a certain statement as something that speaks for itself, that's self-evident. So if I were to convert this into English, this would be basically saying just because, right? So if I were to say that eating a banana is healthy, this is true just because I said so, or something along those lines, right? And the direct proof is basically it uses logical reasoning and establish known theorems and facts to actually prove a particular statement, right? And indirect proof is basically the opposite of direct proof, where proving the opposite of this particular statement is true. Therefore, the statement before that, the not opposite the not opposite statement is true, if that makes sense, right? So the proof by cases, it basically divides the proposition into different cases where you could prove or disprove each particular case separately, right? Then there's the existent proof, which basically out of all the different cases, or out of all the different solutions given a proposition or a statement, at least one of them is true, right? And the opposite of that is the non-existence proof, where basically it finds that in any objects or solutions within the domain of a certain proposition or statement, none of them exactly